So let's review where we are today. I'll highlight what we've covered so far. We've discussed the solar array. We've gone through the PWM with the Basso model. We've looked at a battery model with the current and voltage characteristics that we need for this simulation and the time constant to work within our simulation timing. And today we're going to discuss the error amplifiers, which set the constant current, constant voltage profile for charging a lithium-ion battery. Now we're going to remove the DACs. That just complicates the discussion, so I'm just going to use a fixed voltage and fixed current set point for charging the batteries. So we'll charge a battery to 33.6 volts and we'll have a maximum charge current of 2 amps. So we're just using fixed set points for this, and we've removed the DACs from the model. So here we have the curve showing the constant current, constant voltage charge profile for the lithium-ion battery. We have the 33.6 volts and the 2 amp maximum charge current. We achieved this with error amplifiers that sense voltage and current from the output of the DC to DC converter and limit the maximum end of charge voltage and the maximum charge current. So this is the profile we're using for charging the lithium-ion battery. So here are the error amplifiers. On the left we have a voltage feedback amplifier. It looks at the output, scales the 33.6 volts to 1.25 volts, which is compared against this reference on the error amplifier, and controls the output to maintain 33.6 volts with this error voltage. Same thing on the current side. We have a 2 amp full scale that is scaled with these resistors to make that a 1.25 volts at 2 amps, which comes up to this error amplifier and is compared to that reference to close the loop for current control. Both sides are diode ORed with a pull-up resistor to 2.5 volts, so either side can pull down to control the output should the voltage try to exceed 33.6 or the current try to exceed 2 amps. It's pretty simple, not a lot to show here. You can see compensation parts for the error amplifiers with these resistors and caps on both sides. Those are not optimized for the control loop. I did nothing to improve the AC response. So if you're looking at these and wondering if these are the final values, no, they're not. I have not done any loop stability analysis on this, but I can say from looking at the step response it looks pretty decent anyway. So let's talk about the operating points of the peak power tracker. When we look at this curve, constant voltage, constant current control for the battery charger of the PWM, you can see that we have a closed loop if we could ever reach this line where we're at the end of charge voltage, or we can reach this line where we're at the maximum charge current. In either case, the loops will be closed if you can touch that line. And that just indicates that you have enough power available from the solar array and or the load conditions and the battery state of charge are such that you can close the loop. But if you can't close the loop, then the peak power tracker has to find the maximum power point and deliver that to the battery. The battery acts basically as a reservoir for the peak power tracker. So in that case, you'll have orbits that may be here, or here, or here, or something, depending on what's available. The peak power tracker operating points will be in different locations, depending on what's available from the array and what the load conditions are. But in any case, the peak power tracker operating point must be inside of these curves.